Assalamu alaikum warahmatullahi wabarakatuh. In this lecture, we'll continue section 16.7. In the previous lecture, we finished this problem. Now let's continue. So there is another case here. If we have two gears in mesh, and we mentioned that earlier, that those two gears, if there is mesh between them, then this point of contact, if they are rolled as shown in the figure, here we can say that VB equal VC, and I'm pretty sure that you remember this. Now also, if we want to relate this point of contact to acceleration, then this point and this point move downward with the same acceleration, but not the general one, the tangential one. Okay, so we can say that if there are bodies in contact, consider two bodies in contact with one another without slipping. This is the most important thing. Okay, where the points in contact move along different paths. Then in this case, the tangential component, let me erase. Okay. Then the tangential component of the acceleration will be the same. So if we have two gears or two bodies in contact, then the acceleration, tangential acceleration, the same. So A tangential A for gear A or point A must equal tangential A at gear C, which implies that, so the tangential, we can substitute alpha cross product R, both of them vectors. Okay, so alpha B cross product RB must equal RC cross product alpha C. But the normal components will not be the same. Okay, so we can say that acceleration of gear or gear B at point A normal will not equal the normal component on the other gear. As a result, acceleration for gear B or point A will not equal the resultant acceleration on the other gear. Yes, the tangential, they are equal, but the normal are not equal, so the resultant acceleration will be not the same. Another comment on the rolling bodies. Another common type of problem encountered in dynamics involve rolling motion without slip. Okay, for example, ball, cylinder, disc rolling without slipping. This situation can be analyzed using relative velocity and acceleration equation. So remember when we talked about instantaneous center of zero velocity, if we have rolling body, okay, then the point in the contact with the ground, if there is no slip, then this is VA equal to 0, correct? Okay, and remember the centroid, if it is roll in this direction, then the centroid will have horizontal velocity, okay, as we can see here, as well as it has horizontal acceleration. This is the rule, okay, this is a rule. If we have rolling without slipping, then we have horizontal velocity in positive x direction if it is roll clockwise, okay, and we'll have horizontal acceleration to the positive direction if it is roll clockwise. Okay, now the velocity in contact with the ground, yes, it has zero velocity, and there is instantaneous zero velocity, but regarding acceleration, it's not applied. Okay, so what happens in the acceleration? This point, any point actually in the circumference, will have tangential and normal. But the point in contact with the ground will not have horizontal component. It will have only vertical component or normal component toward the centroid. So when this point before hitting the acceleration downward, and just after leaving the ground, it has acceleration upward. Okay. Okay. So as the cylinder rolls, point G, the center, moves along a straight line. If omega and alpha are known, then the relative velocity and acceleration equation can be applied to A. Okay, with respect to G. At the instance A is in contact with the ground. Okay, the point A here is the most important thing. The point A is the instantaneous center of zero velocity. So point A has zero velocity. However, it is not a point of zero acceleration. There is value for the acceleration, which is the vertical one. Imagine that this point before hitting and immediately after leaving, there is acceleration, but there is no velocity. Okay, here we don't have horizontal acceleration because this is no slip condition. Okay, so let's start with the velocity for a rolling body, and we did this already, but as a reminder, since no slip occurs, then VA, instantaneous center of zero velocity, 0, when A is in contact with the ground. From the kinematic diagram, we can relate this point A with the centroid, so we can say that VG, or we can start with A, equal VA plus omega cross product RG with respect to A. But VA equal to 0, okay? And VG, this is a rule. The centroid has a horizontal component in x-axis only. Then if we substitute here, this is minus K, minus clockwise, cross product. Now I'll travel from A to G positive J direction, this is positive. Okay, then cross product K, cross product J, this is negative I, negative with negative, positive. So VG, yes, it is in the positive direction. And we said earlier that this is a rule. If it is rotate without slip. Now acceleration, how we can derive the equation for VG, or AG, sorry. AG, we need a relation for AG and A in the y direction. This is equal to 0, no slip. Okay, so we need the relation for this equation, and we need another equation for this one, and we'll use them always. Okay, as in here, this is we'll benefit from it and all equation. And here is the rule, no slip. Then the acceleration, since G moves along a straight line path, AG is horizontal. So whenever we substitute relative motion analysis for acceleration, we'll substitute AG positive I direction or negative I direction. It depends. Just before A touched ground, here how we can explain this vertical acceleration. Okay, just before A touched the ground, its velocity is directly downward, and just after contact, its velocity directed upward. Okay, thus point A accelerates upward as it leaves the ground. So this is the point, or this is the location of our interest. So if I substitute this equation, I relate or use relative motion analysis between G and A again. So absolute acceleration AG will equal AA plus relative acceleration in the tangential minus normal component. As we came to know that the centroid has an acceleration in the I direction, positive I direction, and this is in the positive Y direction. As we said earlier, this is a rule. Rotate without slipping. Now, alpha rotate in the clockwise, so we substitute minus, cross product. Now we travel from A to G. From A to G, positive J direction. Minus omega squared R, also positive J direction. Now, if we do the cross product and separate I and J equations, we'll find out that AG will always equal to alpha RG to A, and AA will always equal to omega squared R. Okay, so always we'll use, let me change the color. So always we'll use this equation for rolling without slipping, and for velocity, this is velocity for the centroid. For the centroid acceleration, always equal alpha cross product R relative position equation, or yeah, and this is the acceleration for the point in contact. So VA, this is VG, AG, now this is AA, VA equal to, correct, equal to 0, because this is 0, instantaneous 0 of 0 velocity, instantaneous velocity of 0, instantaneous center of 0 velocity. But regarding acceleration, there is value, which is equal to omega squared VR. Okay, now let's move to question. Now, in this question, what do we have? Gear tools. This is a gear tools. Okay, gear tools on FX. So this is the gear tools on FX rack. This is rack, this one. Okay, with an angular velocity of omega. So omega given, counter or clockwise, sorry. And angular acceleration, again angular acceleration in the same direction. Okay. Determine the acceleration of point A. So we need to find out the acceleration of A, which is unknown. Okay, how to solve? How to solve? Let's see if we have an answer. Yes, we have an answer. Okay, here is the gear, and at the middle we have point O, and on the rim here we have point A. Imagine this is a circular one, sorry for bad drawing. And here we have omega as well as alpha. Now, we need to find acceleration of point A, then acceleration A, if we use relative equation analysis, must equal AO plus AA. We start with A, then, so this is the starting point, this is the ending point, start, end, and this is the tangential component, plus AA with respect to O. This is normal component. Now, before continue, acceleration of point of the centroid from the previous slide is equal to, yes, correct, alpha cross product R. So let me go back to that slide. So remember, here we said that acceleration of the centroid equal alpha cross product R. Okay, so alpha cross product R to 6 multiplied by the radius, which is 0.3, and this is equal 1.8 rad per second squared. And regarding direction, it is horizontal in this direction. It depends on the rotation. This is a rule as I mentioned before. Now, we are ready for calculating acceleration of point A. So acceleration of point A will equal to 1.8 in the positive I direction. This is acceleration of point O plus, or this is negative, so minus 6, because alpha rotate counterclockwise, cross product. Now I will move from O to A. Moving from O to A, where is it? Here. Moving from O to A, we'll move in the positive Y direction. So I will substitute 0.3 in J direction. Minus omega squared. Omega squared in this case, omega given 12. Then this 12 squared without substituting the direction, because this is dot product. Multiplied by 0.3 in J direction. Okay. So this is equal to 1.4. Yes, let me write it step by step. 1.8 in the A minus, this is plus 1.8 in the I direction, and here we'll write minus right away. 0.3 multiplied by 12 squared, this is equal 43.2 in the J direction. And the final answer is 3.6 in the I direction minus 43.2 in the J direction. This is acceleration A. And of course, here we have magnitude and direction. If we need magnitude under root square, and if we need direction, tan inverse of J over I component. So this is question number 1, and we left up with another question. So we left up with this question.